So this is a second set of questions related to haloalkanes. They are all AQA A-level chemistry past paper multiple choice. So I'm going to recommend that you pause on each question and then try it for yourself before you listen to the answer. That way you get to see what your level of understanding is. So let's start with question 1. And in this reaction, we have got a haloalkane. We're reacting it with ammonia. We're making an amine and we're making ammonium bromide. And the mechanism is one of the very important ones that you learn about in year 12. We do 3 different variations of this. And you've got to be able to show it accurately from beginning to end. Let's take a look at this particular question now. Which statement is not correct? Well, ethylamine is a primary amine. For year 12 students, you may not be aware yet of secondary or tertiary amines or quaternary ammonium salts, but those of you in year 13 will know that. The mechanism is a nucleophilic substitution. It is. The NH3 has a lone pair. It's attacking a delta positive carbon. It's nucleophilic, and we are substituting our ammonia for the bromine. Now, ammonium bromide as an ionic compound. It is ionic. We have NH3. NH3 forms a dative covalent bond with NH plus ion to make NH4 plus. And it's actually NH4 plus and Br minus. So that's an ionic compound. That leaves us with our correct answer as the one that's not correct. Actually, the reverse of this would be true. An excess of ammonia would lead to this. Okay, next question. So we're looking at how many different alkenes are formed when 2-bromo, 3-methylbutane reacts with ethanolic potassium hydroxide. Don't be afraid to sketch these out if you need to. It can be very difficult to visualize it in your mind. So if I draw that mechanism out here, you can see the OH minus acting as a base. It attacks the H, it takes the H away. The CH bond is lost, so those electrons move in to form a double CC bond. That then leads to the other carbon losing the bromine, because otherwise it would have 5 bonds around it. And that's a perfectly valid mechanism. But so is this. This is the OH minus instead attacking the H on the other side of the bromine, on the carbon adjacent but to the left rather than to the right. Now that will lead to 2 different alkenes being formed. So the correct answer is A. Next question. We've already spoken about how this mechanism is such an important one. It's very similar to a question you've seen before, so do have a go at it and see what you think, and then we'll take a look. And it is a nucleophile, the NH3. It has a lone pair. It attacks the delta positive carbon. It's substituting the Br, so it is nucleophilic substitution. Just a bit of extra information here. Both of those arrows, though, that will be 2 marks in the exam. The NH3 coming in and acting as a base. Absolutely, it takes that H away. But as we've already seen, and I'm hoping you picked this up from the previous video, the electrons would move towards the electron deficient positive charge. That arrow would start in the same position, but it would move to the N. Next question. So on this one, we're looking at why fluoroalkanes are the least reactive haloalkanes. So we're actually comparing it to other haloalkanes, other carbon-halogen bonds. Now, if we take a look through each of these, fluorine is much more electronegative than carbon. Now, that's true. It's not a false statement, but it's not answering the question. That would actually make it a more polar bond. And if I jump to here, The polarity on C, that would make it more susceptible to attack, so that dismisses A and C as the answer. If we then take a look at B, the F- ion is the most stable halide ion. Now, when you consider the fluoride ion is the smallest of the halide ions, so there is a lesser distance from the outer shell to the nucleus, therefore it's easier to attract electrons in, and it's subject to less shielding, that's simply not the case. So that takes us to the correct answer, D. The CF bond is the strongest carbon-halogen bond, and again we can consider why that's the case. The fluorine is small, so there is very little shielding, so you are going to get that very strong attraction from the fluorine nucleus to the covalent bond, more so than you will with chlorine, bromine and iodine. Correct answer, D. Next question. Got pentane nitrile here, can be made by the reaction of 1-bromobutane with potassium cyanide. What type of mechanism is it? I'm going to point out the magic E here, pentane nitrile. That E is absolutely vital. It will be underlined in mark schemes. You have to have it there. Pentane nitrile will lose you a mark if you were asked to name it. But let's take a look at the question as it actually stands. This is what our 1-bromobutane will look like. Now my Cn- will come in, and my Cn- has got a lone pair and a negative charge. So it has an electron pair that it can donate. Well, that makes it a nucleophile. So it's a nucleophilic mechanism. And I'm completing the mechanism as we go as well. We've now broken it down to a 50-50 chance. We know the answer is going to be C or D. Now, when that Cn- comes in, it kicks the bromine away. So we can say that the Cn- is substituting the bromine, and we're left with the Br- ion. So it's nucleophilic substitution. Correct answer is D.